Welcome to Applied Photophysics Higher Order Structure video series. In this video, we're going to discuss some practical considerations for planning and conducting HOS comparisons. Subsequent videos in this series provide software-specific guidelines for processing and interpreting the data resulting from these experiments using our proprietary Cubic software. Also, if you haven't already, check out our first two videos in the HOS series, in which we took a behind-the-scenes look at the math underpinning HOS comparisons, as well as a few exemplary HOS case studies. Now let's dive in. Maximizing the potential of HOS comparisons requires state-of-the-art instrumentation. Modern CD spectrometers feature solid-state detectors with significantly greater sensitivity than traditional photomultiplier tubes, allowing for the precise detection of subtle spectral differences essential for HOS comparison applications. Additionally, HOS analysis is best performed using automated systems. Flow cell-based CD instruments with liquid handling robotics ensure well-defined, user-independent cleaning protocols, resulting in highly reproducible data. While manual systems can be used for HOS analysis, they often yield lower reproducibility and reduce confidence in the results. The Chiroscan Q100, the automated high-throughput CD system from Applied Photophysics, meets these requirements perfectly. To begin, let's take a brief walkthrough of the HOS analysis workflow on the Chiroscan Q100. Experimental setup is the first and most critical step. Ensuring that your samples are properly plated, as well as choosing the correct set of experimental parameters, are critical to acquiring high-quality, reproducible HOS data. The Chiroscan Q100 is based on a 96 microwell plate format, and samples or sample replicates are typically plated in individual wells and mapped into the software. After setting the parameters and preparing the samples, the instrument can process up to 192 wells across two 96 well plates, equivalent to 96 buffer sample pairs, all entirely through unattended automation. It is customary to visually inspect raw spectral data to ensure no unexpected errors occurred during analysis. Once satisfied, all that is necessary is to run a single software script that will automatically average and baseline correct all sample data, thus preparing the appropriate files for import into the analysis software. Statistical analysis is conducted in Applied Photophysics' proprietary HOS analysis software, Cubic. Some general analysis recommendations are discussed in this video. An overview and usage guidelines for the Cubic software are presented in videos 4 and 5 of this series. The practical considerations discussed in this video apply throughout this workflow. Next, we will outline a few experimental considerations critical to the setup step, and then discuss them more fully in turn. First, it is important to have an independent buffer blank for each sample, as this prevents cross-correlation in the statistical analysis that would result from subtracting the same blank from multiple sample replicates. For example, if you're running 10 samples, there need to be 10 individual buffer baselines as well. Therefore, effectively 96 samples can be run across two 96 well plates. Second, it is recommended to consistently measure the buffer baseline either immediately preceding or following the corresponding sample replicate. This can help in confirming the suitability of the chosen cleaning protocol and the absence of any cross-contamination between wells. This also ensures that sample and buffer blank measurements remain consistent, minimizing the impact of system variations such as background drift that may occur during extended experiment durations. To enable statistical analysis of HOS comparisons, carrying out measurements on several replicates for each sample is essential. Typically, each replicate is an aliquot of the same sample that is individually loaded into the system's flow cell and measured. At least 3 replicates are mathematically required to calculate a standard deviation and establish a quality range for HOS comparisons with reference results. It is highly recommended to conduct at least 5 to 6 replicates to move beyond proof of concept and enable accurate HOS statistics. More replicates may be needed if running samples manually. Ideally, running twice as many reference replicates is recommended, as the reference serves as a positive control for one or more sample comparisons. Ultimately, the number of replicates is often limited by sample availability, especially for near UV experiments, which typically require an order of magnitude more material than far UV measurements. The power behind our Chiroscan Q100 system is derived from the fully integrated autosampler. The autosampler stores the samples in a temperature-controlled environment, reproducibly aspirates and injects the samples into the flow cell for analysis, and thoroughly cleans the fluidics and flow cell in between measurements. The default cleaning protocol is effective in most cases, so developing a custom protocol is usually unnecessary. However, if needed, the cleaning protocol should be tailored to the specific samples being analyzed. Once established, the autosampler will execute it with high fidelity to enhance experimental reproducibility and sensitivity. When using a manual system, such as the Chiroscan V100, strict adherence to a defined cleaning protocol is essential to ensure maximum reproducibility. In our previous two videos, we discussed examples showcasing the power of the weighted spectral difference, or WSD, HOS analysis method. Fundamentally, WSD works by first establishing a quality range based on the reference, and then using the quality range to compare to samples. As mentioned in video 1, this mathematical procedure is conducted sequentially in 2 steps. In the first step, each reference replicate is compared to the average of all the other reference replicates in a pairwise fashion. The standard deviation of these measurements may inform the choice of quality range, such as plus or minus 2 or 3 times the standard deviation. In the second step, each sample replicate is compared pairwise to the average of all reference replicates. In preparation for HOS comparison analysis, a few data preparation steps must be undertaken. Repeat scans are averaged and baseline subtracted using the corresponding buffer blank for each replicate. Both CD and absorbance data are processed in this manner. The Chiroscan Q100 system allows for simple automation of this data processing. CD spectra must be normalized to account for variation in CD intensity due to differences in sample concentration, because we are only interested in spectral differences that arise solely due to structural differences. Normalization is often done based on the absorbance, but other approaches are available. For example, normalization may be conducted by scaling to absolute area under the spectra. Normalization via absorbance is typically carried out at a specific wavelength where there is maximal absorbance. In the far UV, this is typically around 190 nanometers, and in the near UV, this is typically around 280 nanometers for proteins. The average absorbance across a small window, for instance, plus or minus 2 nanometers, is often employed to reduce potential inaccuracy due to noise. In addition, small offsets that might arise from background drift can be accounted for by first subtracting the minimal observed absorbance from the maximal absorbance. The CD spectrum is finally divided by the resulting normalization factor at each wavelength. One factor that can dramatically change the outcome of HOS comparison calculations is the choice of the wavelength range used in the analysis. This phenomenon is particularly acute at the lower end of the far UV range below 200 nanometers, primarily due to significant contributions from buffer components to the total absorbance. As a general guideline in CD spectroscopy, results at wavelengths with absorbance exceeding 2 absorbance units should be excluded due to the limited light availability and nonlinear detector response in this range. It is recommended that absorbance traces should always be recorded simultaneously with CD data for this reason. But regardless of absorbance, users should be vigilant to exclude spectral regions that exhibit high noise and variability. Conversely, longer wavelengths with minimal signal can also be excluded, as they contribute little to the overall results, and recording these areas wastes acquisition time. To highlight the importance of sufficient sample replicates, consider this plot of anonymized data from an actual HOS comparison experiment. Here, the criterion for similarity was defined as more than 50% of replicates falling within the quality range based on plus or minus 2 standard deviations. With only a singleton measurement, there is of course no possibility of conducting a statistical analysis. The interesting result is in comparing 3 versus 9 replicates. The plum samples are clearly different in both cases. However, it isn't clear that the blue samples are in fact statistically indistinguishable from the orange reference samples until enough replicates were run. Again, this is why we recommend that while 3 replicates are sufficient for proof of concept studies, at least 5 to 6, and ideally more, sample replicates be used in HOS comparison studies. The number of sample replicates run and included in an HOS comparison calculation can dramatically affect both the mean and standard deviation of the resulting WSD values. In the example shown here, a study was conducted in which an antibody-based therapeutic was spiked with different amounts of bovine serum albumin, or BSA, representative of contaminants that are structurally different, and with different amounts of an aggregated fraction of the same product, denoted as AG, representative for contaminants that are structurally similar. There were 3 parent experimental groups: MAB references, groups U and W, groups spiked with variable amounts of BSA, groups S, T, P, R, and M, and groups spiked with variable amounts of aggregate, groups O, X, Q, N, and V. 3 identical runs were conducted, each run including 3 replicates per sample. Somewhat different results are obtained when analyzing the data by run compared to analyzing all 9 replicates together. In the latter case of global analysis, only 3 of the sample groups, groups O, Q, and U, lie decidedly within the quality range. More on that topic in a few slides. Let's take another look at the previous MAB spiking experiment, in which groups U and W were the non-spiked references. Although groups U and W consist of the same unadulterated MAB, Each reference group includes only 3 replicates. As a result, when either group is alternately used as a reference, the analysis produces results where different replicates fall outside the quality range, although they are known to be identical. This is because some analysis methods, such as weighted spectral difference, are asymmetric, meaning the results differ depending on whether sample A is compared to sample B, or vice versa. Therefore, selecting an appropriate reference is crucial and should be done in advance. Including 2 sets of replicates for the reference can be beneficial, with one set serving as a positive control known to match the reference. This approach is particularly useful for determining a meaningful quality range, i.e., one may choose to derive the quality range from the reference set with a larger standard deviation, so that the other reference set will conform within the quality range as expected. A quality range must be defined as a cutoff to bin replicates into similar or different categories with respect to the reference. This is a somewhat arbitrary decision. However, typically the quality range is chosen based on twice the standard deviation of the reference similarity values, with ranges of 1.5 to 3 standard deviations not uncommon. Whatever range is chosen must be consistently applied to all data. Experience with HOS comparisons on specific samples over time can help empirically refine the quality range. Additionally, correlating CD data with results from other techniques, such as LCMS or two-dimensional NMR, can aid in defining an appropriate quality range that effectively reflects the differences or similarities being assessed. The final decision to make regarding weighted spectral difference plots is the number of replicates that must lie outside of the quality range for a sample group to be considered different. The choice can affect the final result, as seen here for sample group S. Again, the chosen cutoff must be systematically applied to all groups, and greater than 50% of replicates falling within the quality range is a good starting point. Another approach, which eliminates the need to predefine the number of replicates within or outside the quality range, is the use of the student's t-test and its resulting p-values. This statistical test, included in Applied Photophysics HOS analysis software Cubic, assesses whether the means of 2 groups differ significantly. The application of the student's t-test will be discussed in video 4. An alternative to the graphical weighted spectral difference plot is simply to generate a table of average WSD values for all sample groups. The chosen standard deviation quality range can then be applied to quickly and easily bin sample groups into similar or different categories. For example, the quality range at 2 standard deviations is 0.125, meaning that sample group Q falls just within the category of being similar. The drawback of this approach is that it disregards the variance of similarity values and overlooks potentially significant outliers. A question that frequently arises with weighted spectral difference analysis is whether replicates that fall to the left of the lower limit of the quality range are statistically significant. The answer is no. In fact, these values indicate that a sample replicate is more similar to the reference than the reference replicates are to each other. Although it may seem counterintuitive, this observation is statistically plausible and occurs naturally. Only samples that fall beyond the range on the right should be considered distinct. We hope this third video in our higher order structure video series has been of value to you. Be sure to like and subscribe to our channel to be notified when new videos are released. For more information, including application notes, hardware and software support, and contact information, visit photophysics.com.